All right, welcome back. We're going to be working on area and volume problems from the AP test. These kinds of questions were really prevalent about 5 to 10 years ago. You could almost always count on an area and volume problem, but now it's not quite as prevalent. You might still see it on the AB exam, but if it does show up on the BC exam, it's going to be in a form more similar to what we're going to look at tomorrow. But that doesn't stop us from studying this because these problems still appear on the multiple choice exam. So here we go, area and volume problems. We're going to look at the movie Tron. Tron is an interesting story. In 1982, this movie was released. I saw it when I was probably in third grade or maybe fourth grade. And it really influenced my life as far as, always being in search of the next things in computer graphics and just where this kind of new technology would take us. Funny thing about this movie, though, the computer graphics done in this movie were not necessarily... how do I say this? They weren't. You would look at them today and say, "Wow, this is really kind of cheap and cheesy." But at the time, no other movie had done that much computer graphics, and in fact, they were disqualified for an Academy Award. Not that they necessarily deserved an Academy Award, but they were disqualified on the grounds that using computer graphics they saw that as cheating. So the idea for the movie is that a human gets sucked into the world of computers where he meets, as a user, he meets other programs, and the programs are all sequestered and made to basically destroy each other for the entertainment of humans. Our problem today is based on one of the ending scenes of the movie where the hero Tron is meant to destroy the Master Control Program, or the MCP. This is what it actually looked like in the movie theaters. Yeah, that doesn't necessarily look great. I mean, the MCP, the red thing on the right, that is computer graphics. On the left, that is not computer graphics, although the red luminescent on his outfit was actually hand animated by the studio. So yeah, that doesn't look necessarily inspiring or awe-inspiring or whatever, but most people would probably remember this scene from the video game, which looked like this. And here you see our friend Tron trying to blast out the shield that's guarding the MCP. Well, that's really neither here nor there. As far as our problem goes, so here's the idea. The outer wall of the MCP is modeled by the equations. We got O. Let me blow that up for you. O. That red line. That's the outside wall. And then I, which is the blue line down here, that's the inside wall. And those are going to be, well, eventually they're going to be rotated around the x-axis. But this is a model of the cross-section, or one single cross-section of the MCP cone, or maybe half the cross-section, depending on how you're looking at it. So the first part, A, find the area of R, the area enclosed by the curves I, O, x equals 0 and x equals 2. Part B, find the perimeter of R. And part C, find the volume generated when R is revolved around the x-axis. A good place to begin here is just to find the coordinates of all of the intersections. You could do that either graphically or algebraically. So we're going to do this with our calculator, and if you take a look, we're going to start by putting both of those equations, y1 and y2, into our calculator. That's our TI-84 screen. And then we're just going to say, okay, when x equals 0, what is y1? Y1, I believe, is O. So we have the coordinate 0, 2 and the coordinate 13, 5. Let's see where that is on our graph. 13, 5, or that would be right up here. Oh, wait, I'm sorry, at x equals 2, right? At x equals, no, at x equals 0, 2, and 2, and what is that? 2.6. So that is right. Oops, did that again. That would be right here, 0, 2. And then here's 2 and 13.5, or I'm sorry, not 13.5, 2.6. And our second one would be y2 of 0 is 1/2, and y2 at 2 is 7/10. And if you take a look at the graph, that's right here and right here. So we've got those numbers into our graph. Let's see this next part. Part A. Let's find the area on R enclosed by O, x equals I, x equals 0, and x equals 2. And so this is not that big of a deal. You're just going to integrate O and I from O minus I from 0 to 2. You take a look at that graph again over here. The upper function is O and the lower function is I. This is why you're doing upper function minus lower function from the lowest value of x to the highest value of x. So here, if you take a look at our coordinates, our lowest value of x is going to be 0, and our biggest value of x is going to be 2. You can see that in a couple of different places. So we're just going to integrate. It's nice to do on the calculator because you can just go ahead and, throw that in there. If you have y1 and y2 already programmed, which you probably should, you just integrate that and you get 2.8. So the area of R is 2.8 square units. Remember, I like to write a sentence at the very end to explain what's going on. Part B, find the perimeter of R, the area described in Part A. So going back to that graph of the region R, you can see that we got a couple of vertical lines, and to find the distance of a vertical line, you just need to subtract the y coordinates. So the y coordinate up over here is y equals 2. The y coordinate down here, I think that was 0.6. So in order to find the length of this green segment, that's just 2 minus 0.6. And for this purple segment, now I can't remember what the exact coordinates were here, but you're just going to subtract the y coordinates. So segment 1, 2 minus 0.5, it was 0.5, it's 1.5. That's the length of segment 1. Remember, that's one part of the perimeter. The other part of the perimeter here, 2.6 minus 0.7, that is 1.9. Now the other two lines that make up the perimeter of this are going to be a little bit more difficult. Line segment 3, that's I, and if you remember, that's that diagonal blue line. So we're going to take a look at the coordinates here, 0 and 0.5, and 2 and 0.7. Recognize the fact that this is a straight line segment, so we have the opportunity to use the distance formula that you learned in Algebra 1. Okay, well, what was that distance formula? Well, that's the square root of x2 minus x1 squared plus y2 minus y1 squared. And here you get 2.00997. Try to keep all 5 of those decimal places, or as many as you can, just to combat rounding error that could occur. You need to be correct to 3 decimal places, but any intermediate calculations should be done to way more than 3 places. Okay, so segment 4, that's that wavy red line that we saw at the top. So because this is a function, a curve, we're going to have to use the calculus notion of the length of a segment, which is an integral formula. Before we can continue, though, maybe we should take a look at this. And this is that integral formula applied to the segment 3, which would be the square root of 1 plus dy dx squared dx. Most of the time, these calculations will result in a pretty hair-raising antiderivative. So a lot of times these are just done on the calculator. No big deal. In our case, because our equation was, I think it was 0.5 plus 0.1x, dy dx is 0.1, which is why you see a 0.1 squared right here. So this is 1 plus dy dx squared. Most of the time, your derivative is going to be a function of y. In this case, because we had a linear function, our derivative is just a constant 0.1. Let's apply that same formula to segment 4. The first thing to do is take the derivative of our what's O function. So dy dx is a derivative of 2 plus 3/10 x cosine pi x. The derivative here, the derivative of 2 is 0, but the derivative of 3/10 x cosine pi x, that's going to be a product rule. And when you take the derivative of cosine pi x, that's going to be a chain rule. So try to train yourself to look for that as you take derivatives. So here's that product rule. The derivative of 3/10 x is 3/10. That's what we see in the parenthesis here. Cosine pi x stays the same. Over here we have 3/10 x, which is just the first function here. And then we have the derivative of cosine pi x. The derivative of cosine is sine, or negative sine, so we got negative sine pi x. And the derivative of pi x is pi. So there's our dy dx. I'm not going to make too much of a fuss about simplifying that because I'm just going to substitute that into the formula, and you have the length is the integral from 0 to 2, which is 0 to 2 is x min minus at the bottom and x max at the top. 1 plus dy dx squared dx. Let's see, this is me putting this in the calculator. The derivative is a pretty long derivative, so I tried to show you how that was inputted into the calculator using this top part right here and this bottom part put together. But you get 2.519 if you take the derivative of that. All right, let's write down our work. Okay, that looks pretty good. So we have all 4 segments that comprise the perimeter. All we need to do is add them together. So we add them together and we get 7.929. What's nice about this problem is that it shows you the 3 different ways that you can find the length of a segment. Remember, the first way is if you have a vertical segment or a horizontal segment, you just subtract either the y coordinate or the x coordinate. If you have a straight diagonal line, you can just use the distance formula that you learned in Algebra 2. Anything else that is a curvy curve, you would use a calculus distance formula, which is what we did for segment 4. Next, we're going to revolve around an axis. So, if you remember how to do this, you need to figure out first, where is my axis of rotation? And my axis of rotation in this case is the x-axis. I've outlined that in red over here, and I even put the letters AOR, which is my abbreviation for axis of rotation. It's really important that you know where that is visually. The axis of rotation is below the region R, so it's below both the O function and the I function. Let's think about whether or not our cross sections are going to be disc-shaped or washer-shaped. And in this case, I notice that there is some kind of a space here in between the axis of rotation and our region. Another way to put that is our axis of rotation is not a boundary curve of our region. So if the axis of rotation is not the boundary of the region, we are going to create washer-shaped cross-sections. So this is what a lot of people call the washer method. You'll need the two radii. So the first radii is the distance from the outmost curve, the curve that's furthest away from the axis of rotation, and the axis of rotation. This is just a subtraction of two y-coordinates. So the y-coordinate up here, or any place along the O curve, is just O. Remember, y equals O, so the y-coordinate equals O. And then the y-coordinate down here on the axis of rotation is always 0. So if you'll see, we have the large radius, which I use capital R. Capital R equals O minus 0. You know, and on second thought, maybe using the letter O is not the best choice here because it does look like a 0, but well, that's neither here nor there. Now that we have our outside radius, let's look for our inside radius. There's our outside radius, and our inside radius is going to be the distance from the nearest curve to the axis rotation, and it's going to be a difference in y-coordinates. The y-coordinate up here is I, the y-coordinate down here is 0. So our small radius is I minus 0, which is basically just the I function. So our little radius is I. Let's put this into our formula. I probably should have written down the formula. We'll take a look at that in a second. Actually, it's over here somewhere. Yeah, I think it's right here. If you have the handout, you can just take a look at that. But that's pi r squared minus pi r squared. So substitute that in. Remember, it's important for you to write that down. Show your substitution. If this was an actual AP test, you probably could use the letter OX and the function IX in this equation. Notice pi appears twice. It's pi r squared minus pi r squared. So get that in your head that these are the subtraction of two different area formulas. Okay. In the calculator, we have O and I already programmed into Y1 and Y2. So that looks pretty nice in the home screen. Pi y1 squared minus pi y2 squared. And that's what, 23.241. Okay. So this right here, that, I mean, you know, if I was grading this, I'd have to give you, you know, high marks on this, maybe a 5 out of 5. That looks pretty good. I couldn't ask for anything more, really. So good job. You got this right. Let's take a look at the box here. Let's take a minute to copy that down. You can pause the video, of course. I'll talk through it, and then when I'm done, I'm going to go to check your understanding. So area formulas are always the integral from x min to x max of f top minus f bottom. If you have a region where it's easier to find the area from horizontally, you would do the integral from y min to y max of the right function minus the left function. So that takes care of all of this stuff on the left side. Over here on the right side, this is our volume of rotation. First, we'll start off with the idea that volume is always just the integration of some area formula. If you're rotating a region around an axis, then your area formulas are always going to be circles, which is why we have this pi r squared business. Pi r squared the pi and the r squared comes from the area of a circle. It is not part of the volume formula, so I don't want to see a pi r squared in every volume formula that you do. I only want to see a pi r squared if the cross section is a circle. So Big R, little r, those are all a function minus the axis of rotation, or perhaps the axis of rotation minus the function. Remember, that's going to depend on whether your axis of rotation is below the region or above the region. Above the region or below the region. Right. If you're rotating around a vertical axis, then the O's and the X, or the X's and the Y's change up. I know in class I talk about, if it is a vertical axis, just interchange all the X's and the Y's. It'll be the exact same problem. There are some geometric properties which ensure us that that's going to be true. Check your understanding. This one is from an early AP question. I think this is sometime in the 2000s. So here's our region. We have a region of O and a region of S. So the first part is to find the area of R, and the second part is to find the volume generated when R is rotated about the horizontal line, y equals -2. So here are our 2. For this problem, we're not going to use the letter S at all. So, that I think that was for part C. So the first part, part R, or part A, find the area of R. So identify your top curve. The top curve of R is that red curve, which is f of x. The bottom curve is the blue there, that's y equals 0. X min, that happens when f of x equals 0, or we're going to have to figure out what that is. That's not 1, that's not -1, that's not -2. So in our calculator, we're going to substitute. We're going to put y1 as set that equal to f of x. We're going to find out in our equation solver when y1 equals 0. So in our equation solver, you need to start by seeding or taking a guess, where is that root closest to, where is that intersection closest to, and I'm going to guess -1.5. Okay, I believe this is not the correct answer. No, it is the correct answer. Don't forget that when you do this, you're going to have to put your cursor where my arrow is, right here, and push alpha enter. Alpha enter is the thing that is the key command that makes your calculator solve. So we get -1.373. So this coordinate right here is -1.373. Of course, on the right side, those x coordinates are 0. So we've done everything we needed to do. We found the upper curve, we found the lower curve, we found the coordinate of all the intersection points, which basically helps us find our x min and our x max. So we can put all of that into our equation and just solve. Here you see I've gone ahead and written down a equals -1.37312. You'll never have to write that number again. Just use the letter A. And then if you write down b equals 0, you'll never have to use that number again. Just use the letter b. So we got the area equals integral from a to b of f of x minus 0. I can use f of x because you'll notice that the problem tells you what f of x is. And if the problem says what f of x is, feel free to use f of x. You don't have to write down the entire equation. Okay. There we go. Integrate it, and you get 2.903. Not bad. Part B. Let's find the volume when we rotate this this region around y equals -2. So first of all, let's draw that y equals -2. I've gone ahead like I always do. I always make the axis of rotation red, and there it is at y equals -2. Now that I've done that, I already have the intersection points of the region, I'm going to try to figure out which one is the big R and which one is the little r. Actually, let me back up. Does this require a washer method or a disk method? And notice that that red line, that's not even touching the region. So it definitely can't be a boundary curve of the region R. So we're going to create cross sections that look like washers. This is a place for the washer method. Here's our big radius. It's the distance from the outmost curve to the axis of rotation. And this is f of x minus -2, or just f of x plus 2. The inside radius, this is interesting because the inside radius is always going to be y equals 0 for every point along the region. Across here, the y coordinate is 0. So we've got 0 minus -2, which is just 2. Put both of those into your paper, write them on your paper. Yet r equals f of x plus 2 and r equals 2. Volume is always the integral of an area. In this case, our area looks like a washer. So it's a pi r squared minus pi r squared. We have our formulas for our radii. And of course, a and b, that's already that negative 1.373 and 0. So all we need to do is put this in our calculator and calculate it. It looks like we're going to get 59.361. Okay, so your volume is 59.361405. Lastly, you might want to write down a sentence of explanation. Part A, the area of the region is 2.903 square units. Part B, the volume of the solid is 59.361 cubic units. And that's it. So that's our review of solids and areas as you might see them on an AP test free response. And I will see you guys next time.